talk to us about the real world.
Kind of. Yeah, well, thanks for coming to my talk. I'm Josh Christie. Today I'm going to talk to you about how we at Fugro Roames are classifying large-scale point cloud data, kind of how we're processing our point cloud data in Julia, and what we've learned along the way. So some background, the company that I work for, Fugro, collects vast amounts of data and analyzes it from ships, planes, drones, trains, and cars. And we use that data to provide intelligence to our customers, such as, for our power lines. So Roames, our office in Brisbane, was born out of a need to try and understand how our power lines in Australia are interacting with the world around them. So vegetation, it's challenging to manage. It grows, it falls, and in extreme conditions, it's unpredictable. If you think about the 2017 Californian wildfires that claimed the lives of 43 people, it's devastating. So our solution to this problem is to digitize the network. We do this by flying over the power lines, collecting Lidar and imagery data. We then model the network, identifying the power poles, the power lines, the vegetation, buildings, and other objects such as cars. We can then report back to our customers, such as when the vegetation is too close to the power line or when a power pole is falling over. We've processed data here in the US, across the UK, in Europe, and throughout Australia. With several petabytes of data that we've collected, and last year, just in that blue area, we collected 100 billion points, and we processed and classified it. Manually doing that would just take far too long. So we've been investing our efforts into doing our point classification in Julia. So here's a video of the results that we're getting. You can see the different colors represent different classifications. So green for vegetation, the beige color for buildings, and the power lines have been later, we've applied a mapping to the voltage of the power line. And we've also, you can see that's dependent on the distance from the power line and the voltage of the power line. We do our processing in the AWS cloud, and that just allows us to scale up for the large amounts of data that we process. We're also classifying the more components on the pole top, and we're classifying cars, but it's not shown in this visualization because the customers, So I mentioned before that we collect Lidar data. Lidar is a method of collecting an object in 3D. Imagine on the bottom of a plane if a laser is mounted and the laser emits a light. The time that it takes for the light to reflect back from an object can then be used to work out the distance of the object. And if you have a GPS attached to the plane, you can get all the points accurately georeferenced in the real world. Doing this at over 400 kilohertz a second creates a high resolution 3D world from the skies. So on the right, you'll see that's an unclassified point cloud with the intensity from the reflection of the object applied. So you can kind of see like the 3D world. So now I'm going to describe a bit about how we're processing our point clouds, and I'll give an example of a feature and a classifier that we use. So on the left, typically a machine learning workflow would look something like this. You have the raw point cloud data, and you derive some features about the data, such as the height of a point, or by calculating PCA, which I'll explain soon. And then you train a classifier model and predict off that model. You'll notice the Julia colors in there. So loading a point cloud, I'm going to go into a bit about the optimizations we do and kind of what we've learned. So loading a point cloud in Julia is suboptimal, just as an array. So we've utilized the package static arrays, and you can represent it as an array of static vectors. I'd highly recommend giving static arrays a go if you're working with lots of smaller matrices. So assume you've got all the points loaded into Julia and you wanted to do some spatial queries such as find me all the points within 1 meter. There's some great packages out there such as the nearest neighbors.gl package and the use of KD trees. Well, we found that by just gridding the points in an XY plane and ordering the points by height gave an approximate 20% improvement. And it also allowed us to easily abstract to other geometry searches. This is probably largely due to the 3D nature of the point clouds. So I mentioned before that we use PCA can be used to describe the shape of a point cloud. It's typically seen in exploratory data analysis where you want to decompose a multi-dimensional data set into small dimensions and you want to visualize the data. But it can also be used to describe the internal structure by comparing the eigenvalues. So you get a measure of how linear, planar, or spherical a set of points are. So here's an example of computing PCA in Julia and using the static arrays package. So you can see in line 1, computing the covariance matrix. And we're utilizing static arrays, and that largely allows you to do the same operations as you would with the standard array. So that's seen in lines 2 to 6. And then static arrays also provides the function eig with specialized code for static arrays. Overall, this was about 40 times faster than just using a standard array. We've had a lot of success using the xgboost.jl or xgboost classifier, and there's a package in Julia that allows us to call the C++ code. It works by building up an ensemble of decision trees. And each tree on its own is not powerful, containing only a few branches, but through gradient boosting, it improves the mistakes of previous trees, adding, improving, and ultimately making the model better. So here's an example of the final results of all the classes that we're currently classifying. So we're detecting buildings, power lines, cars, cross-arm streetlights, road. Yeah. Thank you very much. Check out our website if you want to find out more. Are there any questions?
Thanks for your talk. I have a couple questions. Like, I imagine you refly every now and then to keep an eye on what's happening.
Yeah, that's right. Yeah. Generally, it's like once a year.
Okay.
Yeah.
And are these analyses you do completely independent, or do you?
So we do some modeling of the vegetation to see the growth of the vegetation. You can do forecasting on when you expect it to cut back, and this allows the operators to optimize their network. And in Australia, it's really massive, and people have to drive into outback for hours. So you can kind of optimize, knowing it's not going to grow that much there. They don't have to go every 6 months or whatever. They can go once a year.
Okay. And how about dealing with larger than memory data sets? Do you do any kind of streaming processing, or do you tile it all? And
yeah, we tile our data and we process the data in tiles, and that's just it's pretty standard kind of map reduce example. Yeah.
So are you guys doing any of the Lidar to point cloud, like the signal processing in Julia, or is that done in some other?
No, we're not doing it in Julia yet.
Is that on the roadmap?
Potentially. It's in C++ code. It's a big investment, but yeah, it's an option, yeah.
Any more questions? All right, let's thank Josh again.
Thank you.